Hello, my name is Hannes, and today I want to talk to you about processing IoT data using AkkaNET. Now, how many of you do have any, even hello world experience with AkkaNET? Okay, for you guys the first part might be a little bit of a repetition, but it'll get more interesting after the first half, right? So what are we going to do today? First I'm going to give you an introduction to what AkkaNET really is. And I'm going to tell you which problem I tried to solve when I was writing the code, and which role AkkaNET plays in that solution. And then I'm going to tell you a little bit, I'm going to get a bit more detailed and show you a little bit of code and how I did some of the things. And then I'm going to try and point you towards a future if you would like to continue using this. Now, like a lot of things in programming, the first idea about actor models came in the 1970s. I don't know if it was because people were less distracted by their smartphones or because they did better drugs than we do. But a lot of the stuff that we're using today was invented in the 70s, and actor models are no different. In 1973, Carl Hewitt and Peter Bishop, they wrote the first research paper that led to what Akka and AkkaNET would become. And during the years that followed, there were a lot of follow-up papers by other people, which led to, in the 1980s, Ericsson. Ericsson was in the phone business, right? Who remembers having an Ericsson smartphone? I do. Well, it wasn't a smartphone, it was a dumb phone, right? But they were in the telco business, and the way that they earned money is by making phone connections between people and charging them by the minute. So if those connections fail, you're losing money. Which meant uptime was extremely important. And they wanted to design a new switching system. It was the AXD 301. And to do that, they decided to use actor models. But there wasn't a programming language capable of doing that. So they actually wrote their own, which was Erlang. Still exists today. And that has the actor model built into it. And they used that to write about 2 million lines of code to write a very fault-tolerant and distributed across multiple machines and very concurrent telco system. And they reached 9 nines uptime. Now, I don't know about you guys, if you see this number, if you really know what that means, but to put it into perspective, that is about 31 milliseconds of downtime a year. Now, that's some impressive numbers, right? So the resilience that they got from the actor model really worked for them. Now, to get to where AkkaNET comes into the picture, in about 2010, we had the first version of Akka on the JVM, using Scala as the programming language. And in 2013, 2 people individually started porting it to the .NET CLR. They were Aaron Stannard, the guy who sent me the sticker, so thanks, Aaron, and Roger Johansson. And at some point, they learned about each other's effort. And they, in early 2014, they decided to pick one code base and work on that. They took some parts from both implementations and continued there. And they asked permission to Lightband, the company behind Akka on the JVM. They got permission to actually call it AkkaNET. And that's why in 2015 we had our first stable version. But more happened in 2015. As .NET developers, we were really spoiled because we basically got 3 actor model implementations in less than a few months. Microsoft released Project Orleans, which they used to write the backend for Halo 4. And then the guys from Petabridge, Roger and Aaron, they actually released the first version of AkkaNET. And then also Service Fabric Reliable Actors was released a few months later. Now that put me to wonder, it's like, why 2015? I mean, these ideas have existed since the 70s. The first implementations have been around in the 1980s. Why on .NET only in 2015? And basically it was because the classic ways of scaling applications didn't hold up anymore. We had the explosion ever since Apple released the iPhone and we had an explosion of internet usage. I mean, every smartphone app that booms triggers millions of requests to the backend. And if you scaled in the good old website days, you probably had a setup that looks like this. You had a load balancer over here, and then some web servers, and maybe a cluster of database server with a write master and some read slaves. And if that couldn't keep up, you would add a cache cluster, right? And that would be your production environment. But at some point, you are so overwhelmed by requests that even this gets really hard to do. And the thing is, until then, we basically got a free lunch. Because as our applications grew and our user base increased, we could just buy the faster machine, because every year we got faster processors. But in the processor market, a lot of things happened as well. This is like 42 years worth of processor clock speed, number of transistors, and so on. But there's like 3 trends from that graph that are really, really important. The first is, like, processor clock speed has stabilized for more than a decade now. We used to have 5 gigahertz processors. I remember that you could overclock a Pentium 4 from 1.3 to 5 gigahertz if you used liquid nitrogen. That was like early 2000s. That has been possible for more than a decade. And you can also see that the single thread performance of all of our processors is also flattening out. It's still climbing, but not as much as it used to. Which means that if you want to take advantage of the one thing that is increasing, the number of cores, which started increasing around the first half of the 2000s, if you want to take advantage of that, you're going to need to parallelize your code. And if you want to run parallel code, you're going to need to think about programming differently. Because I don't know how many of you have tried to manage your own thread pool on .NET. But that shit is hard. It's really tricky. And the thing that hurts you most are things like shared state. Because as soon as you need to share a little bit of state between your threads, that means that you're going to need to implement locking somehow. And that can lead to deadlocks. But in the best case, even if you don't have any deadlocks, it means that there is going to be a portion of your code that will not be parallel. Access to this resource will always be serialized. And serialization is the thing that hurts your scalability. We have Amdahls law. Amdahl basically expressed how much speed up you can get from adding more resources, adding more CPUs to a system that needs to process a fixed workload. And he does this in relation to how much of the code can be parallelized. And if you have 50% of your code that cannot be parallelized, it means that it doesn't matter if you throw 65,000 CPUs at it, you're not going to get more than a divide by 2 increase. You'll get 2 times faster. And even at 95%, it's still depressingly low. Because at 95% parallelizable code, you're still never going to reach more than a 20% speed increase, a 20 times speed increase of what you're doing. So 90% parallelization is never going to cut it. And that's where the actor models come in. Because they will try to get you a very, very high degree of parallelization for systems that hold state. Because as long as you don't have state, having multiple threads is really easy. I mean, that's basically what a web server does, right? But as soon as you need to do things with data, the parallelization becomes harder. And that's where the actual actor models try to help us. They do this by using very reactive patterns. And the side benefit is that you can make it very fault tolerant. We'll get to that in a minute. I'm going to tell you how. Anybody know this book, by the way? Yeah? I love Randall Munroe. The What If book was amazing. I put off reading this. It's actually in my bag in the hotel. I want to start reading it this week. But how? If we're using Akka.NET, there is the fundamental building brick of all of our code is going to be an actor. And an actor is actually a very, very simple object. And the goal of the actor is to hold its own state. So all of the state that this actor needs should be internal to the class. It should just be private properties, right? Aside from that, this actor will have an inbox. It's not something you need to implement. It's something that the actor system does for you. But the messages from this inbox are dispatched to your actor one by one, which has a very, very great benefit. All of your actors will always run single-threaded. There will never be multiple threads on one single actor. Which means that inside your actor, you don't need to worry about resource locking or whatever. You can use all your own private state as much as you want. Nobody will get in your way. Which means that you don't have any concurrency problems, right? How does that look in code? This is like the simplest actor you can write. You inherit from the class untyped actor and you implement the onReceive method. And the onReceive is just what the actor system calls whenever a new message is dispatched to your actor. And you can do whatever you want with it. And if you just check what type the message is, you can process it. That's quite easy, right? I don't need any further explaining. All of you .NET developers will get that. And even the ones who do Java will just understand this quite fine. But then the next thing is the messages, because at some point we need to get messages to our system. Also, these will be very, very simple objects. The only thing is that you really need to take care of when you're using Akka.NET is that your messages should be immutable. The content should never change. And the tricky thing is that Akka.NET does not enforce this in any way. I'll try to explain a little bit. Is if you send a message to another actor that lives on the same system, the message is not serialized and deserialized. It just passes the object reference. Which means that if the other actor is actually processing that message, you could still change the content from the other actor. You shouldn't, but you can. Now, as soon as you pass a machine boundary, that no longer works. So you shouldn't try to exploit this, because if you grow to the size where you need a whole cluster and not a single machine, all this behavior that you're exploiting, it will break anyway. And it goes against all the ideas that are behind the actor model. Now, the throughput of these is really, really great. The people from Akka.NET, they claim 50 million messages a second per machine, which is quite a lot. I can, without breaking a sweat, my laptop does about 1 million messages a second, and that takes about 10% CPU, so I have no reasons to doubt these numbers. So how do you do that? The immutable messages, you make properties that only have getters, and you set them in the constructors. Those properties can never change. But if you want to do that for something like a collection, you cannot change the collection reference, but you might change the content of the collection. And then you still have a mutable message. But you have the system.collections.immutable namespace, where you have things like immutable array, immutable list, stuff like that. And then you have a immutable message again. It makes sense to do it like this, because then you can never forget and you can never mess up, right? And then there's the actor system, because now you wrote some actors and you wrote some messages. And then at some point we will have to coordinate all this code, right? And these actors, they will come to life, you will create them. And at some point the messages need to be put in an inbox, and the messages need to be dispatched from the inbox to the actor. And all the threads in the machine needs to be scheduled. Remember, that's what we want from the system, that it does that for us. So basically you got to think about it like the big puppet master that keeps all your actors in the air. Still by far the best Metallica CD ever. The actor system is something that you really create really easily. You just go actor system.create and you give it a name, and you're done. Your actor system will be running. There is a little bit more to it than that, but that's about what it does. And then to create your first actor, you use props. And this comes from a philosophy that you should never hold an object reference to your actor. You should always have an iActorRef. And this props is basically a pointer to the constructor. So you can pass in some parameters here, and they will get passed to the constructor of your actor. And then you go actor system.actorOf, and what you will get back here is an iActorRef. And that's basically all you need to talk to another actor. If you have an iActorRef, that's how you send them a message. And all you do is, to the actorRef, you go tell, and that's all that's needed. The message will go to the inbox, and you will be able to talk to them. Now, actors live in a hierarchy. There's 3 actors that you get for free in the actor system. It's the root actor, the user, and the system actor. And all of the actors that you make yourself, they will go under the user actor. And the ones that you create directly under that, they are the top level actors, and they can spawn children. And your position in the hierarchy defines your address. Just like an HTTP address, an actor has an address. So the one here at the bottom right is /user/a2/b3. Now, the thing is, how many of you have children? Yeah, a few of you do. I have 3. What is the problem with children? If they fuck up, you're still responsible, right? Exactly. So that's what you need to do. If you go with your children to the supermarket, you have to supervise them. If you spawn child actors as an actor, you need to supervise them. And the way this works is if an actor throws an uncaught exception, the exception gets escalated to the parent. And the parent will receive a message that says, okay, you need to handle this fault, what do you want to do? And the parent actors, they will have some kind of supervision strategy. They can either escalate it to the grandparent. Usually you don't have to do that often. Or you will decide on what to do with this failure. And you can apply the philosophy, the thing that you're going to do, either to your one child, the one that fucked up, or to all your children at the same time. That makes sense if you cut up a huge workload that is worthless into a lot of small pieces, and you dispatch them all into children. If one of them fails, it doesn't matter. The others don't need to complete. You want to kill them all, maybe. Another Metallica song. You can do 3 things. You can either resume the actor, which means like, okay, we don't care about this exception. Continue as you were. And it will just continue with the next message. You can tell it to stop. It's like, okay, you messed up. This is really bad. I just stop what you're doing. I'm going to kill you. And we might spawn another of you, but you're done. And you could just decide to restart. And that means that your inbox is saved. The same message will get dispatched to the new actor, but you just recycle it. Which means that your state is gone. You have to rebuild your state again, but you will get the same inbox and no messages are lost. Now these are the basic concepts of using an actor model, and that means that you have to think about your development a little bit differently. Every workload that comes in on your system as a whole, you're gonna want to split that up into much smaller tasks. So if an actor spawns a lot of children and dispatches work to them, and they spawn more children and they dispatch the work to them, then you have a lot of small units of work that can get scheduled on the threads of your actor system. Also, you want to put risk to the edges. If you see here, if an actor fails at the bottom of your hierarchy, you can just recuperate from that, because its parent, B3, will actually solve that one and hopefully come to a state where everything is peachy again. Maybe the database connection failed or whatever. If you have your risky operations only at the bottom, you won't lose a lot, right? And it also pushes you to use different design patterns. And the guys from Petabridge, they have a lot of training about AkkaNET. It's worth it at some points. But there's a whole training about actor design patterns. If you're really serious about using this in production, it's something that they also have blog posts about. You should really read up on. But there's one that I found so funny that I really want to hand it to you. It's the character actor. Are there any Star Trek fans? I'm also more of a Star Wars guy, but in Star Trek, what happens if you have a guest actor, like somebody who plays like 1 or 2 episodes and they're really famous? If they go to a new planet, they're the guy that they send down. And he dies. But that's okay, because that means that the main cost can live on. And that's basically what you do with actors. If you know that I'm going to do a risky operation, you're just going to spawn a child actor and push the risky operation down on that. If that one fails, you can just like restart it and all your state is going to be intact. That's the character actor pattern. There's a lot of them, but it's the one that I wanted to really give to you because it's really important. I think that puts you, is there any questions about this part? I think that's enough theory about how it works. I want to get more into what we try to solve and go into IoT, right? So, what we're looking at, do these look familiar to you guys? This is what they look like in Belgium. It's like electricity, gas, water, the meters that you have in your house. And notice that all of these just display a number. It's your consumption probably since the moment that the meter was installed in your house. Now, what we want to build at some point is some IoT device that connects to this meter and gives us the values and sends them to the backend so that we can use that data to provide some kind of value to our users. Now, the first thing that you have to think about is, are we talking about readings or are we talking about consumption? Because all these meters, they show a number. But we don't really care about the number, right? We might have bought the house 2 years ago and all the consumption that happened before that, we don't care. What we care about is how much are we using, which is the difference of meter reading between the previous reading and now. That's your consumption, and that's the thing that you're actually going to care about, because that's what you're going to get billed for. If you give the electricity company your meter readings, they will just diff it from last year, and then they will tell you how much you need to pay. So what do we want to do? We want to compute consumption from the meter values. We want to store those values so that we can present them to the user as graphs, or that we can do historic analysis on this data. And also we want to provide the user with alerts. If you consume more than a certain amount for a certain amount of time, that's something that you want to maybe have a pop-up about on your phone. This is the few use cases that we want to talk about in the rest of the talk. You can have a momentary threshold. That's really easy. If you consume more than 90 kilowatt hour an hour, that's maybe when you want to be notified on your phone. But that's momentary. That's only at 10:30. It gets more tricky if we're talking about consuming more for 20 minutes. Because at the red line, you have exceeded this value for 20 minutes straight. That's really clear-cut case. That's going to be an overconsumption. But the green line is something different. Although it is not exceeded every 5 minutes, we still exceed it on average. What do you want? And that's a business decision. It's not something that I can decide for you. There is no right way. It's something that you will have to talk to your product owners about. So if we want to build this, we want to see how we can use AkkaNET to do that. And your typical IoT stack will look something like this. If you work with IoT devices, I put some Azure services on there for reference. You're going to have basically three main parts. The first part, which you can use IoT Hub for, is all your device communication. Your devices need to authenticate. You need to detect if they're online. You need to do presence detection. And you're going to need to capture events that come from the device to your backend. And at some point, you might want to send control back. Turn on the lights. Set the thermostat set point, whatever. Now, this is something that is handled very well by that product. And then all the data that comes in on the event stream, you're going to want to process somehow. And there's a bunch of Azure services that you can use, but mainly it's all these compute variations that you can use to process that data, to shape it, to enrich it, whatever. And then you don't have any business value yet. The real business value comes from doing something to your users. So you want to give them some kind of dashboard that they can look at, and you want to give them a way to get alerts on their phone when something goes wrong. Now, AkkaNET won't solve all of that. It mainly will help you on everything that is compute and analytics, but all the outside services like talking to the devices and so on, there are better solutions to do that. You could hack it to do so, but there are basically better ways. So how does that look if we try and visualize what the main components of the system would be? Is you would have an IoT hub, for instance. There is on AWS, there's also some you can use, that does all your device communications for you. And how many of you are familiar with IoT Hub? Only a few. Okay. IoT Hub has a built-in event hub, which is basically a little bit like Kafka. It's a huge event stream where you can have your own pointer and read your messages individually, and some other consumer can have their own pointer. The messages don't disappear like a queue when they're processed. You just remember where you were. This has a huge advantage of not sending them directly to Akka.NET and have a service in between. If you put an app service between your IoT hub and your Akka.NET cluster, you can basically at some point decide to pause the processor that is in the middle and redeploy your cluster, because at some points you're going to need to ship new features, right? And then turn on the sending again. And you will get a decoupling between the two because of that. It makes your life a whole lot easier. And then your Akka.NET cluster will basically push stuff to storage, and your web portal can connect on the cluster and ask for data and interact with that as well. Now, don't be a magpie. Who knows about the magpie? It's this black and white bird, it likes shiny things, which is a myth, but doesn't really matter. We all know the image. We developers are like magpies as well, right? We like the new shiny thing, want to do it everywhere. Think about where you're going to use this. Okay, if your system is very stateful and you need to process lots of threads, those are two really good reasons to use an actor model. If you're building a static website, this might not be for you, right? And it doesn't have to be your whole solution. So, what do you need to do in implementation-wise to make this work? Because it's time that we get to the real business. The first thing is we need to get our messages to the actor system, because as I showed you in the previous diagram, the actor system was running on its own, and as I showed you in the code earlier, we would just go actor system.actor off to create an actor. So we're going to need something that is called remoting. Actor systems can talk to each other, even if they live on another machine. And your local actor system doesn't have to have too much stuff in it. You can just make a local actor system, not put any actors in it, and still talk to the remote actor system. But it gets better if you do. And the way this works is there are multiple transports that you can use. The most common one is to just use TCP between your actor systems. And then your host actor system will open up a port, and all the other ones will connect to it. And the addresses, if you use TCP, they look like this. So you have a protocol, you will point to the remote system, where it lives, on which host, and then you will point to the address of the actor. And you can just talk to that like any actor that lives on your local system. This gives us the advantage to do something like this. On the left is the app service that we use to read our event stream from IoT Hub. And on the right is the remote actor system, which is our Akka.NET cluster. And on the client actor system, we will have an actor system in this app service. There we will spawn a proxy actor that will talk to the device actors that will actually live on this side. Because the big advantage of doing actor systems altogether is that you can model the real world. So a device in the real world will be an actor in the actor system. If you have a proxy, that means that if we read the stream, we just ship the messages to our proxy there, and that one talks to the real actor. Which gives us the added benefit that that one can detect network failures and so on, and we can have supervision on that again, and everything becomes really reliable again. But how that works is if we are first talking to a device that we haven't had before, we will create a proxy actor. And that one will go to the top level actor here it's an orchestration actor called devices, and it will just send a message something like hello or connect. That will trigger that one to see if one of its children is actually the appropriate actor or not. If it's not, it can just create a child. That's okay. And then it will reply back with an actor reference. It's like, hey, Kate, this is the reference of the actor that you should be talking to. And this is something you can store. And the cool thing is that this is completely location transparent. The devices actor doesn't have to know where the call comes from when it passes on this actor ref. If it ends up on that site knows that it should go over the wire over TCP. That's something you need to do zero programming for. And from then on, that proxy can just talk to the device actor directly, which is one of the big, which is how you avoid this devices actor, the top level one, from becoming a bottleneck actor. Because if you ship your entire event stream through that actor, you're gonna end up with an inbox that is like way too full on that side. And you still have a single thread on that actor, and you're gonna be limited by that. So this makes sure that a lot of the workload is actually going directly to all the individual device actors, which is really what you want. It makes it really parallel. Now in code, these next couple of slides have a lot of code on them, and I'll try to explain a little bit what happens. Every actor has a pre-start method that you can overwrite. The device actor proxy, this is the proxy actor. That one will basically use an iActor selection. Now you can use wildcards in that. So an iActor selection is a way to select a bunch of actors into an actor system. If you pass it an address that is unique, you will get back a selection that contains a single actor. But if you would want to talk to all the actors that match a certain pattern, you could do that as well. But it's a lot slower than using a real actor reference. So we could use an actor selection to talk to our device actor on this side. But what we really want is an actor reference, because that's a lot faster. So we will just use the actor selection once to find the devices actor, the user devices one, and not the real device actor. And we will send that one a connect device message with the device ID. And we will get a message back that says device connected, and that one will actually contain the real actor reference. And that one we're just going to store in a private field, and that's how our proxy can communicate over the efficient path using the actor reference. Now, the rest of this proxy, we are using a receive actor and no longer an untyped actor. It's another AkkaNET class. It makes writing your code a bit cleaner, in my opinion. Because in the other one, you remember, you got an object message in your onReceive, and you needed to dispatch it yourself to all the methods that handle them. If you use a receive actor, you no longer have the onReceive method. But in the constructor, you can just set up which types of messages go to which functions that need to handle them. This is a lot cleaner, in my opinion. And if our device actor proxy gets in a meter reading from the event stream, it can just pass it on with a tell to the real device actor that lives on the other side across the wire. That's how we get our messages to our device actors. There's one thing that I want to give to you. It's the thing at the bottom. The people in the back are maybe not going to be able to see it. I write a create props method on all of my actors. Because if you remember, this props.create, it just has a params array of objects. And that needs to magically map to the constructor that is right here. But it's not strongly typed. So if you change your constructor, everywhere where you don't call the props properly, it might break when you're creating a new actor. So you don't want that. So what I do is I make the static method to create props for this particular actor that really maps on that constructor. If I refactor it in this place, I add a parameter at the top and one at the bottom. All the rest of my code, where I call the props for these actors, it will break, and it makes the refactor a whole lot easier. it's something you should really consider doing. Now in the device actor, the devices actor, that's the top level actor, when we get a connect device request, we're just gonna see if our device dictionary contains the device ID that we are requested to connect to. And if it does, that's really easy. We can just respond. Otherwise, we will actually create the device actor. And the thing is, what you'll see here is we will use the device ID in the name of the actor that we make. If you don't pass any real names, it will just generate a name for you. But addresses in the whole hierarchy need to be unique. And what we have is a lot of device actors that are at the same level, so they all need unique names. So it makes sense to just use the ID of the actor in there to give them a unique name. Now, we no longer want to spawn our actors as like top-level actors in the actor system. No, we want to spawn them as children of the actor that we're working in. And that's what we have the context for. In every actor, there is a context property, there is a parent property, there is a sender property, which is the one that you're actually getting the message from. And all of these are filled before the message is dispatched to your actor. And because it's single-threaded, they won't change during your execution of your message, and you can just use these properties. And the context is what you use to spawn a child actor. You don't need to do anything else than that. This will be a child of the devices actor. And as soon as we have that actor ref, we can just pass the actor ref back to the sender, which is on the other side of the wire, which is the device actor proxy, and that's how they talk to each other. There's not more to it than that to use Akka remoting. Now the next thing that I want to talk to you about is normalizing messages. The thing is, when you're dealing with data, like this, the customer's internet connection will go down, which means you will lose data. The serial connection between the meter and your IoT device, it might go down, which means you will lose data. The serial connection is very finicky, and it might not have error correction on it, so you might get bogus data from time to time. Now, if you allow all that data to flow into all your business logic, you're going to be dealing with that at a lot of different places. So what you typically want to do is to first normalize all the data that comes into your device before you pass it on for processing further down the chain. It will save you a lot of time. And there's a couple of things that you might want to do. The first thing is timestamp correction and bucketing. Not all the devices that you talk to will have the possibility to have very correct times when you read values, and most of the time it's not going to be a problem. But it might be a lot easier if the rest of your system knows that it will get a value exactly on every timestamp every 5 minutes, and that will contain the consumption for the past 5 minutes. So if you get all these values every minute on the left, you might end up with normalized data on the right that looks like this. And that will make it so much easier to think about all the rest of your logic if you have that. Now the size of your buckets is going to depend greatly on what the business cases are that you're going to have. At some point you want to have very, very granular data. And 5 minutes might not be enough at all. At some points you might want to go to 15 minutes even, because that's as small as you need it. Now what also happens is you're going to need to fill gaps, because at some point some measurements will go missing. How do you want to fill that gap, and do you want to fill it? There is no right answer, but you can fill this gap in at least 6 ways. You can basically decide not to fill it, or you can decide to see it as one big value because you don't know where this consumption happened during this time, during these 3 periods that you're vague about. And you can put that peak at the start or at the middle or at the beginning. you could just take that huge value and just cut it into 3 even pieces and just put those in there, and then you will have a flat line for the duration of the gap. Now, if the gap is like 15 minutes, that's probably going to be okay, but if the gap is a day, that might look completely wrong. Or you could follow a trend line. You could see that the top one here, and then there's a bottom one there, and you would follow the line between them and split it out like that. That would also maybe work. The problem is these are all wrong. I mean, there is no correct way to do this. And the closest you might actually get is to look at the same time period last week and follow that same line. You could do that. It's a lot more intensive to do so. But even that will still be wrong. What you got to decide is which one of these will yield the least artifacts for the business case that you have. And maybe it's important for you to actually notify the downstream services. You might decide to use that one. Just split it evenly, because that's the easiest to implement. It's like divide by 3 and just ship out 3 messages for 3 consumption buckets. But you might want to notify downstream services that this data has been gap filled. So you might want to add a property on that message to let them know, like, okay, don't trust this data completely, it was not a real reading. Maybe you can get away without doing this, but it might happen. I'm just giving you the idea. Now, how do you do that if our device actor gets in a meter reading? It will forward the meter reading to another actor that lives below that, which is the value normalization actor, which will be a child of our device actor. And that one will basically do the gap filling, it will do the bucketing for us, and it will pass normalized messages back to the device actor. You can just go parent.tell and the message will end up at the device actor again. And then that one can dispatch those normalized messages to all the other actors that are going to need the values. If you need to do storage, if you need to do alerting and so on, you can work with the normalized values instead of with the raw meter readings. Makes life a whole lot easier. Now at some point you're gonna want to write data to disk, because as I told you, the state lives as private fields in objects, which means if your process recycles, all your data is gone, which is typically not what you want. Now, AkkaNET has thought about this before, and they have something called the persistent actor. It's basically an actor that can persist its state to a number of data stores. You can go from I think you can use Azure Tables, you can use a normal SQL database or MongoDB, there's a whole bunch of options. But the whole system works the same regardless of what storage technology you pick. Every actor that needs to persist state to outside the actor system, it's going to need a persistence ID. It's like its unique key in the persistence system. And then it can just call persist, and it's a bit of an event-sourced system. And all of you familiar with event sourcing? It's like you store events and then you play them back later. You can persist every event that comes into the actor, and then if you restart the actor, you will get them all back. And that works fine if you have 25 events, but it doesn't really work if you have a couple of million events per actor. So at some point you're going to have to take a snapshot, and then your actor will get the last snapshot that it took, and then you will get all the events that happened since the snapshot, and then you will have restored your state. To look at it in code, so every persistent actor needs this persistence ID. We set it in the constructor and we use the device ID as an ID because that makes sense, right? And this is what it will put in the column in the database or in the property in the database that stores your persistence ID. And from now on, we don't have a receive anymore, but we will have a command and we will have a recover method. Command is what you use for messages that come in the regular way. Your system is operating and you receive a message. Recover is when a message comes in from your recovery system. So if this actor recycles, before it starts accepting messages, it will actually restore its snapshot. It will replay all the events that were saved to disk until that moment, and only then will it accept messages from its inbox. So that's what these recover methods are for. And for the snapshot, you also have a recover for the snapshot offer message, which is a type that's provided by Akka.NET itself, and that's how you can restore your snapshot. Now, what makes thinking about the persistent actors a lot easier is if you make a class that holds all the state for this particular actor. And you just call it like your state class, your device persistence state or whatever, and everything that you want to persist in your snapshot, you put in there. Then you can just do your snapshots like this. Every 100 messages, I'm going to do save snapshot, and I'm just going to put my state in there. And that will get serialized into the data store. And then when we get the snapshot offer that's on the next slide, we can just like replace the state object and we're up and running. Every command that comes in, we're going to actually persist it and call another method at the same time. And that's something that Akka.NET does. If the persistence failed, it will not call the other method to make sure that everything stays consistent with the data store. You persist it, you write it to the database, and then you will call this function where you do actually everything that you want to do with this type of message. Which is the difference in behavior between the real command and an internal processing of the recovery. Because the recovery will call this one directly. This one changes the state. This one also persists it to the database. And you don't want to persist the ones that come in from recover, because then you will end up with an infinite loop. And if you get your snapshot back, you just check if it really is of the type myState, and if it is, because that's always the first message that you're going to get on a persistent actor, you can just replace your state. Very easy. At some point, you might want to start looking at if saving your snapshots are successful or not. Usually, you don't really need to know. Because the side effect of what happens if you're saving your state is something that happens asynchronously, your snapshot. If it fails, it means that the next restore will just get more messages after it restores its last snapshot. So usually it's not a huge problem. But at some point you might want to know, and you can handle the snapshot success or the snapshot failure events, and then you can do something with that knowledge. Now at some point, this data is going to become huge because our meters, they spit out values every minute of every single day. And probably our system to operate, it's only going to need the data of maybe the last 12 hours to do alerts. All the rest you can fetch from the data store if you need it. So at some point, you might want to truncate your state objects. Your state objects need to become a bit smaller to keep in memory because all of it lives in memory. And you want to offload the historic values, the things that happened before the interval, for future reference. So you will end up with something below your device actor that looks like this. You will have a value storage actor here, and that one uses regular persistence, the way that I explained it to you just before. And that one will just, when it truncates its state, it will actually offload it to another actor that will write to maybe another data store to safeguard the values for historic usage. Which means that only the state that we keep here will get restored when the system reboots, and that's actually what makes sense. And the last thing that you're going to need to worry about is how we're going to deal with system restarts. Because you cannot make all your actors persistent actors. That would really hurt your performance. So what you would want to do is basically you recreate your actors and you have them query the one actor that has all the data from the database. So when the system restarts, every device will recreate its value storage actor, and that one will actually replay the snapshots and all the events, and then it will have a state for the last 12 hours or so. And then when you create a value normalization actor or an alerts actor or whatever, they will just query the value storage actor with a message like, hey, give me the last 25 values. And that will just reply back. And that's how you get all your actors stateful again when your system restarts. Makes it easy to do that. I'm going to conclude with a few more things because we're almost out of time. If you want to move on from this, there's so much things that I didn't talk to you about. The first dry run that I had about this talk was 3 hours. That would have been boring. But you're going to need to do a lot of things to get your actor system production ready. There's this thing called HOCON configuration to configure all the persistence, remoting, and so on aspects of your actor system. So you're going to need to get familiar with that. If you want to run your actor system across multiple machines and then shard your actors across them, there is a module for that called AkkaNET clustering. It's not that hard to do. So you're going to need to get familiar with that. If you want to run it in production, you're going to need logging. You could use dependency injection to inject stuff into your actors. The guys from Petabridge sell a very good production monitoring system for it. That one is not free, Phobos, but it's really good. So these are all things that you're going to need to do if you really want to move this to production. You also might want to start learning about AkkaNET. There is a free bootcamp on GitHub made by the people who actually wrote the framework. It's really nice. It's where I started. There's a bunch of stuff on Pluralsight if you have an account. The Petabridge blog is like a gold mine. They blog about pretty much every feature they release, and it's all still up there, so you can learn about pretty much everything that is in the framework and the modules. And if at some point you find yourself stuck, it might be worth going for the paid remote training, but because they do it in small groups and you have a lot of opportunity to ask questions to the guys who have a lot more knowledge than I do. You're also going to need to think about deployment. What I told you about earlier is you might want to pause the ingress of messages, wait for your actor system to stop processing, redeploy it, restart it, let all the persistence recovery take place, and then resume sending of messages. You're probably going to want to script this if you want to have continuous delivery. But if you do this right, you will lose no data whatsoever with your deployments. So to conclude, check if your problem domain actually fits the use of actors before you dive in. And decide which part of your solution you're going to use it for. And then you design your actor hierarchies appropriately, using the right design patterns, making sure you avoid bottlenecks, making sure that you have persistence in the right places, that you have recovery, and so on. Normalize your data, it makes your life easier, and think about how you're going to do deployment and recycles. It's time for questions. My name is Hannes. This is my Twitter handle and my ICQ number. Believe it or not, that still works. I wrote a huge repository. Well, it's not huge. I wrote a repository that basically implements everything that I talked about today and a lot more. You can find it on my GitHub. Clone it, play with it. There's a lot of stuff that you can learn from that. Do you have Slido questions for me? Because we have like 7 minutes for questions, right? 6. You have a question?
When you persist a snapshot,
yes.
you actually clean up the events or the data prior to that snapshot?
It does not, but it flags them in the database. So the question was, because the people in the back might not have heard, if you persist the snapshot, does it clean up the events in the data store? It flags them as irrelevant. So there's a flag, I think it's called isDeleted. See me in the hallway, I'll show you, I have it on my laptop. Which is set to 1. So you know that you can clean them up, but the system doesn't clean them up for you. But you can make a cron job that like every day throws away all the events that happened yesterday and that have been flagged as no longer relevant. So you know what you can clean up. The system doesn't do it for you.
They also do an actor placement strategy in an actor cluster. How would you determine where that
Okay.
actor is going to be brought up?
Basically, if you spawn a child, that will go onto the node that you were on unless you define some form of sharding. And then you can, for instance, shard on your device ID and distribute all the device actors across your cluster. There's a very nice, do you have a Pluralsight account? There is a whole course about Akka clustering on there where all the sharding and so on is explained. But you have control, remember that. Any more questions? No?
So what's the debugging story? Because it seems like it could be a problem.
Debugging is actually surprisingly easy. If you're attached with a debugger, you can just put breakpoints everywhere. But it's the same as with any event-based system. It's also always hard to reason about flow. If you get a message that is dispatched on your actor, you really don't know what original message came into your actor system that triggered another actor to do something to send you this message. That is a little bit trickier. If you want to know this, there is a practice where you could add correlation IDs to your messages. You add a GUID to the incoming message and everything that comes from that, but it's something you're going to have to do yourself. You can add that correlation ID and then you can basically trace it throughout your system. If you implement logging if you do this and you implement logging with Seek, for instance, you will have a lot of insights in how that happens.
Do you have any tips for testing actors?
For testing actors, yes, there is an AkkaNET test kit that allows you to mock everything that is the actor system, the sender, the context, and so on. And that basically makes it quite easy to completely mock all the actor system parts, and you can very easily unit test them. So, and especially if you use dependency injection to inject logic into your actors, that comes a really testable system. More questions? That's going to be a philosophical question, I think. The big advantage, the thing is, if you use event sourcing, you're usually, whenever you process a command, you're going to load them from a store. The thing is that once this is running, all your state is in memory. So you're not going to be chatty with the database with this at all. That might be the big decider between the two, whether you need that or not.
How do you ensure your mailbox is durable?
They are not. So yeah, if your system crashes, the stuff that was in your mailboxes, that's gone. So you're going to have some kind of strategy to replay that. You can have feedback loops. And that's one of the advantages of using an event hub or an IoT hub, is because your message stream that feeds the system isn't gone. So you can basically replay from wherever you want. If you make all your message processing idempotent, it doesn't really matter how far back you put the pointer, it will just work. But yeah, that's like the production questions that you're always going to have with this kind of system. Okay, I'm going to let you guys have some coffee. If you have more questions, I'll be around all week. Just hit me up in the hallways. I love talking about this stuff. So just ask me. If you want an AkkaNET sticker, they're right here. And don't forget to vote on your way out. Thank you.